Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the output work of fuel cell. Some reactions can be made to approach reversibility by having them take place in an electrolytic cell as shown in the figure. When a potential exactly equal to the electromotive force of the cell is applied, no reaction takes place. When the applied potential is increased slightly, the reaction proceeds in one direction, and if the applied potential is decreased slightly, the reaction proceeds in the opposite direction. The work done is the electrical energy supplied or delivered. The fuel cell contains an ion exchange membrane that separates an electrolyte from the reactant and product gases. In the basic fuel cell, hydrogen and oxygen gases are supplied separately, so the hydrogen gas enters at the anode, where it dissociates into atomic hydrogen and further into hydrogen ions and electrons. The hydrogen ions travel through the membranes or electrolyte, and the electrons through the external circuit, and they combine again with oxygen and the cathode to produce water. There is an electrical potential difference between the anode and cathode, and the flow of electrons constitutes a current, which is how the electrical work is delivered to the external node. Consider a reversible reaction occurring at constant temperature equal to that of its environment. Based on equation 1335, the maximum work output of the fuel cell is, where delta G is the change in Gibbs function for the overall chemical reaction. We also realize that the work is given in terms of the charged electrons flowing through an electrical potential E(S). Thus, for a given reaction, the maximum electrical potential E0, or the reversible electromotive force of a fuel cell at a given temperature, is. In practice, however, many fuel cells operate at an elevated temperature, where the water lives as a gas and not as a liquid. Thus, it carries away more energy. The computations can be done for a range of temperatures, leading to lower EMF as the temperature increases. The ideal EMF for a hydrogen-oxygen fuel cell as a function of temperature is shown in figure 14.5. A variety of fuel cells are being investigated for use in stationary as well as mobile power plants. The low-temperature fuel cells use hydrogen as the fuel, whereas the higher-temperature cells can use methane and carbon monoxide that are then internally reforming into hydrogen and carbon dioxide. The most important fuel cells are listed in Table 14.5, with their main characteristics. The low-temperature fuel cells are very sensitive to being poisoned by carbon monoxide gas, so they require an external reformer and purifier to deliver hydrogen gas. The high-temperature fuel cells can reform natural gas, mainly methane, but also ethane and propane into hydrogen gas and carbon monoxide inside the cell. The latest research is being done with gasified coal as a fuel and operating the cell at high pressures like 15 atm. And the fuel cell has exhaust gas with a small amount of fuel in it. Additional combustion can occur and then combine the fuel cell with a gas turbine or steam power plant to utilize the exhaust gas energy. These combined cycle power plants strive to have an efficiency of up to 60%. The maximum efficiency for a fuel cell is given by 14.6. Okay, that's all for this task. Thank you very much, and see you next time.